Hello, fifth graders. We're going to be doing the inquiry activity on page 209 of your Be a Scientist notebook. So if you want to follow along or you want to do this at home, I'm going to kind of do it right here for you. And this is an easy experiment. If you have the stuff to do it at home, do it at home. It's fun. It's cool. I love this stuff. All right, so we've been studying physical properties of different things. Now, physical properties are when your matter changes, like states. Physical properties can also be the color of things, the texture of things. Elsie, shut it. Anything that doesn't have to do with a chemical change where something else is created, where there's a different kind of matter being created besides what you have. For example, salt water. We get our water, we get a little table salt, sodium chloride, we put it in, we stir it up. That's a solution. The water hasn't changed, the salt hasn't changed. It's just salt and water. There's no chemicals. That's a physical change. And so we're going to be doing states of matter today, freezing water to see if the matter changes, any difference in matter in the mass between liquid water and frozen water. We're also going to look and see if maybe perhaps, I don't know, will the volume change? I don't know. So let's first read our instructions here in the inquiry activity called Frozen or Unfrozen. This is page 209. All right, first, does the mass of matter change when it changes state? Make a prediction. What do you think? Do you think the mass and the volume of water will change when it freezes? Why or why not? If you want to write this down and follow along with your prediction, make your hypothesis, pause the video right now. I'm just kidding, I'm still going. But you can pause it right now, make your prediction, write it down, and then resume, and then we'll read the directions. 3, 2, 1, pause. I'm paused. Okay, no, you pause. Okay, never mind. Anyway, make your hypothesis. Now we'll go on. This is Baby Yoda. Shut your bone hole. All right. This is Baby Yoda. He's going to be helping us out today. So, first off, what we need identical plastic sealed bottles. I am using these. These are for coin collectors. It's just easier for me to use this kind of stuff. I have this laying around. You can use whatever you want. Mason jars are fine. It doesn't matter. With water, here's my water. And of course, a pan balance. I don't have one of those here at my house, but I do have a scale. Scales is fine. And a marker. It's a marker. Also, get out your collection of graduated cylinders and, your medical syringe, because we all know that we have these laying around the house, okay? No, I'm just kidding. You may not have it, but it doesn't matter, because whatever you do, however you're going to fill your stuff with right here, you just make sure that you're using the same amount for each one of these. You're going to put 2 together, so you want to use the same amount of water. So it's easier for me to do it with a medical syringe. My wife's a nurse, you know this. She keeps this stuff around. I can fill this up easy. It doesn't matter. You can use measuring cup, things like this, whatever. Just put the same amount in each receptacle. They have to be exact same receptacles too, like this. All right, so number 1, measure and record the mass of the bottle of liquid water in the table. Well, I've already got one of them done. I'm going to do the second one right now. I'm going to fill it up. I've been using 20 ml. But first, before you do your second one, cap and all, mass it, So my empty receptacle is 12 grams. Now if I put 20 mil in here, you should know how many grams that water is going to mass. Please, you do remember this from the third quarter. Remember, water is 1 gram per mil. So if I have 20 mil, it's going to equal 20 grams. But let's just see if it actually does. So if that's correct, this should be somewhere around, and 1 gram here or there for a little over or a little under 1 gram is not going to make too much of a difference. But let's just see. 32 grams, I'm right on spot. 20 grams plus the 12 grams of the container, that equals water in the container is 32 grams. And look, it just changed, so it's probably somewhere like 32 and a half, somewhere around there. Here's my second one. I'm gonna make sure that this is marked. I don't quite have the same amount in here. I might need to add just a tad more. It's always hard to get it absolutely exact, but we'll see if we can. You want to make sure it's the same amount of water on both of them. That looks like the same amount. If you can get down at eye level, it's about the same amount. So this should be about 33 grams. 33 grams. Okay, each one of these is exactly the same. Now what I'm going to do, I'm going to cap it off, and I'm going to make a mark where my water level is. Right there. That will tell us if the volume is going to change when it freezes. I'm going to put it in the freezer here in just a second. Turn that off. All right, so measure and record the mass of the bottle of liquid in the water. We did that. Examine the 2 bottles side to side. There we go. Record any differences in apparent volume by looking at height of the surface of the water in each bottle and the shape of each bottle. Record this in the table. Now I'm going to go ahead and write down right here, liquid water, and your numbers are going to be different than mine. That's okay. Liquid water, the mass is 20 grams. The apparent volume, 20 mil. Now, here's what I'm going to do. I'm going to take one of my bottles. I'm going to leave the other one here. This is going to be my control. What does it control? A control is, in an experiment, the control is the one that we don't do anything to, that we take all the measurements with. It's going to be our normal one. So here is our 2 bottles. The control, going to stay here. We're not going to do anything to it. This is the one that we're going to freeze. So we're going to put this right in the freezer, and we're going to give it some time, and then we're going to come back, and we're going to see if it's frozen, and then we're going to look at our line that we drew right here. Look at our line that we drew, see if it went up or down. What is our prediction? I'll say, thank you. All right, we're going to, she likes to get the last word in. All right, so we're going to see if it goes up, down, or it stays the same. What's your prediction? Where is it going to be? Is the volume going to increase or decrease? What do you know about ice? Does ice float in your glass of water, or does it sink in your glass of water? You might want to take that into consideration when you make your prediction. That's just me. Put it in the freezer. And the ice cream, of course, falls out and hits you in the foot. There we go. Now we'll wait and see what happens to it. Is it frozen yet, Baby Yoda? All right, some time has passed, and now we have a frozen water. Take a look at the line. Did it do what you predicted it did? Did you say that it was going to increase in volume? Because it looks to me, get some of this condensation off. All right, now let's compare it with the other one that we did nothing to. And take a look at the levels there. Well, it's pretty clear that the frozen one actually increased in volume. I wonder if that has anything to do with what I said earlier in envisioning what the ice in your drink does. So let's come on over here. Now, what is your prediction? Do you think that this is going to be more than 32 grams, like it was at the beginning? Or is it going to be less or more? Well, some people would think just because now there's more volume, now it has to have more mass. But let's find out. We'll do our control again. It's right at 32, 32 and a half. Now it says 33, so it's about 32 and a half. It's about where we were last time. And now our water that's frozen. Well, looky there. And as you can tell, I can take this up and then put it back down. So it's registering 33 and sometimes 32, and there it goes back to 33, so it's about 32 and a half. It is the exact same amount frozen that it is in liquid. This is called the law of conservation of mass. When matter changes shape in either liquid form, right here, same amount. When you take away energy to it, like putting it in a freezer, it solidifies. That's called the freezing point. The freezing point, there's the same amount of matter than there was before. But it increased volume, but the mass still stays the same. Still stays the exact same. Now, what would happen if I took this and I put it on the oven range and turned the heat on and turned this into water vapor? How much water vapor, when I boil all of this away, how much water vapor will I have added to my environment? Well, if we have 20 mil of water and 20 grams of water, then when it boils completely away, we've added 20 more grams of water vapor to the atmosphere. All right, so right now I want you to take a look at page 210 of your Be a Scientist notebook. There's some questions about what happened using your prediction and what actually happened with our little experiment here. Feel free, like I said before, feel free to do this one at home. There's going to be some other experiments that, well, you're not going to be able to do at home, and some experiments later that I'm going to do that that you can, and I'll be sure to tell you what you can and cannot do at home. But for right now, let's look at page 210. And while you're looking at that, I just kind of want to make a little, let's call it a little mini lesson about temperature. Now we have Fahrenheit, degrees Fahrenheit, and we have degrees Celsius. Okay, so I'll draw a little thermometer right here. Not a very good one, it's all right. And let's say water freezes. Now let's say water boils right here. Bring it over here. And water freezes here. All right, now the difference between Celsius and Fahrenheit, it's kind of weird. It's strange. The United States, Belize, the Bahamas, a couple of other small countries use Fahrenheit. Every other country in the world uses the metric system, which is Celsius. Water freezes. Celsius is modeled after water. So we all know that water freezes at 0 degrees Celsius and 32 degrees Fahrenheit. Now that's the same temperature, just measured in two different scales. Think of it as like inches and centimeters. Like a yard is 3 feet, and in that 3 feet there's 12 inches, but a centimeter is smaller than an inch, and then you have like 100 centimeters in a meter. They're different ways of measuring, but they're measuring their length. This is measuring temperature. So when we talk about water boiling, based off of water, Celsius is 100 degrees is when it boils. In the Fahrenheit, it's 212. Now you might ask yourself, why is there so many funny numbers here? Well, Fahrenheit, which is his name, he was a scientist. Fahrenheit modeled his scale off of salt water freezing, and the salt was not the salt that we find in the sea. It wasn't sodium chloride. It was ammonium chloride. You're probably wondering what ammonium chloride is. Soda ash. Soda ash is something that you might put in a pool. If you have a pool, soda ash is put in the pool to balance the water, make sure it's not too acidic or too basic. Soda ash is also an ingredient found in different foods that you might eat. I'll look that up and see what kind of food you might have tasted ammonium chloride in. Doesn't sound too good with ammonium in it, but it does taste different than ammonium smells. But anyway, Fahrenheit based his off of a different scale than Celsius. Celsius is easier for scientists to do because it is dealing in water. Some things we talk about freezing, and I might melt some lead here in a little while to show you that the melting point of things are different. Melting point of water is 32 degrees. If it's ice below 32 degrees, once it reaches 32 degrees, it starts to melt. There are metals that will melt like at 3,000 degrees. So it doesn't necessarily have to be cold. Different matter has different melting points, different boiling points, different freezing points. All right, so let's take a look at our 210. If you're not done with it, you can pause the video right here. And now we're back. So we can answer some of these questions. Did the freezing water change its mass? Explain. Well, no, it did not change its mass. Remember our law of conservation of matter tells us it's actually starting to melt. You can see the ice moving in there. So that's cool. And we have condensation. That's for another day, though. The amount of matter in here has not changed. It's still 20 grams of water. Still 20 grams. So the amount of mass has not changed. Did freezing the water, number two, did freezing the water change its volume? Why, yes, it most certainly did. And while we still have some frozen water in there, we saw a huge amount of change. It's already frozen a lot, and our line has gone down from where we saw it just a little while ago. But the volume did change. It got higher, which means it expanded more. Well, why did this happen? Well, we have water molecules might look like this. Now everything else, just about everything else, when it goes from liquid to a solid, like this, will contract. Water is different though, because water tends to do this when it freezes. And this is just another property of water. Its molecules will organize itself into shapes like this. And so it actually increases its space between the molecules. Very few substances actually do that, but water is one of those things that actually does expand as it freezes, and it expands as it boils. Think about it. If you took this liquid and you put it in a pan and you boiled it, you're creating now gas. This would be the liquid. This would be the solid. Now your gas particles are going to be going off in all directions and moving away from one another, sometimes bouncing into one another. It will expand as a gas. It will expand when it becomes a solid. However, like I said, just remember, this is one of the few types of matter that actually does this. Most of the time when something becomes a solid, it compresses, it becomes smaller. All right, so what does the activity tell you about how matter is conserved in a physical change? Well, you have the same amount of matter. Same amount of matter in this one, the same amount of matter in this one. So when it changes from one thing to another, it's still got the same number of molecules. Same number of molecules in here, same number of molecules in here. Doesn't matter whether it's expanding or contracting. It doesn't matter. Still the same amount of molecules in each one. So how would you make the frozen water melt faster? How could you do this? What could you do? More energy or less energy? You should have said more energy. That's right. You can take this, and we could. Why don't we try? Let me see if I can get this out, and I can get this out. So let's just come over here for a minute. Heat, more energy. Watch that for a second. It's melting a lot faster now than it was before. Don't do this at home, please. Melting a lot faster now than it was just sitting there. That's because we're adding heat to it. We're adding more heat energy. More energy to this is going to make it melt faster. It's almost gone. Don't try this at home. I have guitar finger calluses. I can't feel it. And hey, how about that? It's gone. Look at it. It's gone. So now what I'm doing is when you start to see all the little bubbles in there, see the bubbles? Now we're getting to its boiling point. Now all of those water molecules are separating even further, turning into water vapor and coming into the air. And we may not be able to see it happen sometimes. There it is. You can see the water vapor now, if you look really carefully. We're adding water vapor to the air. Now, we just increased the moisture level of the air in the room. Now, if we boil this all the way to where there's no water, that's dangerous. Don't do that. And it will destroy the pan if you did that. So don't do that. But if we did, we would have added, look at it evaporating and drying up right here on the side. We would have added whatever our volume, whatever our mass was in the first place, which was 20 grams, 20 mil. And I am not going to ruin Mrs. Johnson's pan by doing that. So we'll just, oh, look at all the water vapor. Awesome. If you have any questions, you can always class dojo me on this stuff. I will link a video to my website that I thought was really cool about this, Mr. Fahrenheit, and how he came up with this. Nobody knows for sure. It's kind of a myth. Nobody knows exactly sure. Now let's think about what we just did. Now we saw the volume increase as the water turned into ice. Okay, so let's think about our control first. The density of water is 1 gram per mil. We have already proven that. Our density equals mass over volume. Come over here and look at this. Density equals mass over volume. So for our control, it was 20 grams over 20 mil. What is 20 divided by 20? It's 1 gram per mil. We already know that liquid water is 1 gram per mil. Now, we don't quite know our volume of the frozen water, but we can kind of take a little bit of a guess. The mass was still the same, 20 grams. I say we increased it by about 5 mil. That's about where it was. So let's just say it was 25 mil. Let's look right over here. Now when we do our equation, 20 grams over 25 mil, that is equal, and y'all can do it on calculator if you don't believe me, 0.8 grams per mil. This is ice. Now, it being less than liquid water will tell you what? Does ice float or does ice sink in water? It most certainly floats. So your ice is less dense than liquid water. Probably best if I just put 1 in there, or 2. There we go. See, and that's why the ice floats in your glass of water or iced tea or whatever you have. All right. If you have any questions about this lab, this was a very cool lab. I'm probably going to be doing most of these labs in here that I have the equipment for here at home. I will be doing. I'm also going to be supplementing that with other cool experiments and explaining why things work the way they do. But if you have any questions on this specific lab, you can class dojo me, or you can email me with any questions that you might have. Like I said, you can do this at home. It doesn't matter what your containers are. If you want to use something like this as a bowl, or like any kind of glasses, cups, or mason jars are good. As long as you're putting the same amount of water in both containers, it should be just fine. And you will get the same exact results. So if you have any questions about this, go ahead and let me know. Probably going to be doing a video in the next day or so going over, let's see, the answers to the questions on pages 212 of the Be a Scientist notebook and page 213. So we'll be going over these in the next couple days. Remember, if you want to, it's highly recommended that you do the Mastery Connect quizzes. There's no grade on it. It's not a requirement, but You need to know these things for middle school, so make sure that you do them. So until the next video, Baby Yoda and myself bid you a fair adieu.